Hello and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. In the previous module we were discussing electricity, little bit of history of electricity and magnetism. Now we will complete that history and then show you what Maxwell's equations look like. Remember, we have already introduced you to the first electromagnetic quantity, which is electric field, and electric field surrounds any charge, and this electric field would be varying at every position as well as it could be varying with respect to time. If the fields are time invariant, then we call them as static fields. If the fields are varying with time, we call them either as time varying fields or dynamic fields. And parallel to this electric field is the notion of magnetic field. What does a magnetic field do? Let's assume that you have two current carrying wires. We introduced this one previously, and then there is one more current I2, this other circuit is carrying. So there is a complete circuit here and then there is a complete circuit out there, correct? Of course I have not shown you the sources of these currents, okay, but imagine that there are these two sources somewhere sitting up there. Now it has been observed that if you focus your attention only to this small segment, okay, to small segment, that depending on whether the currents are going in the same way or the currents are going in the opposite way, there will be either attraction or repulsion between these two pieces of wire, okay. And coupled with the fact that this current can change the magnetic compass deflection, it can introduce deflection into the magnetic compass, people what they did, there are a lot of people who worked on this one. The important ones are Ampere and Biot and Savart. What they found was that each small piece of current carrying wire actually develops a magnetic field around it, okay. So there is a magnetic field that is developed by this current, and it is this magnetic field which was deflecting the magnetic compass, because compasses are known to deflect. So this is a magnetic compass. This magnetic compass would deflect slightly only when it is perturbed or when it is kept in a magnetic field. So if there is a surrounding magnetic field, then this fellow will be perturbed a little bit, or it would be deflected like this, and that magnetic field was created by this current carrying wire. And the amount of magnetic field that would be produced, and magnetic field is a slightly different beast than electric field, in that the magnetic field, if we call this B as a magnetic field here, sometimes B is also called as magnetic induction, but don't worry about that, we call B as magnetic field. Sometimes we also call another quantity which I will introduce as magnetic field, but the context usually will make you clear what we mean by what. So we have electric field. Let's denote the electric field here first. So this electric field is a vector, therefore it is E with a bar on top of it to denote that this is a vector, and it is a function of both position vector as well as time. And this magnetic field component, I don't exactly remember the formula, but it also has interestingly a square like behavior, but then the direction of this magnetic field produced by the current element. So if there is a current element of I, okay, or I1, maybe if you are looking at the effect of the current I1 circuit, there will be along this length there will be a certain line element dl. So there is I1 dl cross r hat, okay, where r hat is the unit vector at which you are actually trying to find out the magnetic field of influence. So this is the magnetic field of influence. So at this point, if you were to look at this r, then the magnetic field will be a quantity which is actually perpendicular to both dl and r. So this cross that we have written between dl and r tells you that this is a cross product, and the magnetic field is actually given by the so called right hand rule, that is, you curl your thumb or you curl your this one in such a way that you try to enclose your magnetic field, the direction of magnetic field, when the direction of the current carrying wire is along my thumb. So this is the thumb. Circling this thumb will give you the magnetic field that is surrounding this particular current carrying wire. So this is my current carrying wire, and this is the magnetic field that would be present. So you can see that from this equation as well. In this equation you have dl, which is along this direction, and then r, which is the unit vector along this direction. Perpendicular to both will be the direction of the magnetic field. There is a little bit of a cheating going on here. That is because currents are not line elements. You can't take a current piece and then isolate this one and say, okay, this is my total current I, because current always has to go into a complete loop. Okay, but nevertheless we call this law as Biot-Savart law, and this is used in calculating magnetic fields. Closely associated with this one, the closed loop kind of a scenario, is what is called as Ampere's law, and you would probably see Ampere's law in this particular manner. I will explain to you what this is, but this is what you would actually see Ampere's law. So let us label this as Ampere's law. Okay. Whether it is B here or another quantity, I will explain to you in a minute. What does this mean? This means that if instead of considering the current in a small element, if I actually consider a path, okay, over a closed path, okay, and then evaluate the magnetic field around this, then this magnetic field, over this particular path, the complete path will actually give me the current enclosed by this conduction path. So these two laws are slightly different in the sense that one law allows you to determine the magnetic field, the other law tells you that if you were to take this magnetic field and then integrate it around a closed path, what you will see is the result of this integration is actually a total current that is enclosed. Okay. Now these are all very nice, and you can actually do this in certain scenarios, which is essentially called as vacuum, or in this particular magnetic field case that there is only one magnetic the current carrying wire, and then you have done this one. But if you were to try and do these experiments in a material medium, remember we have already talked about material medium and dielectric permittivity. Associated with magnetic field is also a very similar phenomena. Okay, you do these experiments in air and you do these experiments in a magnetic material such as a ferrite or something, then the result would change slightly. So as before in the previous case, we introduce what is called as permeability. So we say that the better is the permeability, the better is the magnetic property of that one. The permeability of free space is denoted by mu naught, and this is given by definition, this is given by 4 pi into 10 to the power minus 7 Henry per meter. Okay. So this Henry indicates that this is a concept introduced or linked with inductance, and therefore the permittivity, just like permittivity was linked with capacitance, permeability is linked with inductance. Okay. So this is what mu 0 is, and in a material you will have mu 0 and mu r multiplied together as the overall permeability of the material. Okay. So what is this permeability that we are talking about? The full discussion is slightly complicated, I won't go into it, but then the field quantity B is related to another quantity called as H. Okay. This H is what we sometimes call as magnetic field, and B is sometimes what we call as magnetic induction, or sometimes called as magnetic flux density. Okay. Unfortunately there is no standardization of what we call as what. B is what is called as magnetic field by most physics people, okay, whereas H is what we call as magnetic field or magnetic field intensity by most electrical engineers, and magnetic induction is a slightly older term for B, and magnetic flux density is because it is similar in many ways of its behavior to electric flux density, which we will introduce very shortly. Okay. So we have, in a matter of few minutes, we have seen three electromagnetic quantities. One is the electric field quantity ERT, and then there is a magnetic field quantity BRT, and then there is another magnetic field quantity, or rather magnetic induction or flux density. Okay. And then this H is called as the magnetic field, okay, or simply the H field. This we will call as simply the E field. This does not introduce a lot of controversies over here. So simply call this as E field, B field and H field, and you can be alright. Okay. The way in which you measure E field is volt per meter. Okay. The way you measure this H field is ampere per meter, and the way you measure this B field is the unit called as Tesla, after the great scientist Tesla that you might have heard of. Okay. And what are the laws that is satisfied by this? The electric field at any point is given by the force per charge q. Of course, in this equation you should remember that the charge should not be very large. Okay. The charge should be barely enough to correctly estimate the electric field because of a certain charge that is already present. So this is a test charge, okay, and the test charge magnitude should be very, very small. Numerically, of course, test charge, if you set it equal to 1 or 1 coulomb, because charge is measured in coulomb, then E will be equal to F. okay. And the laws that are linking B is linked to the current, E of course is linked to the force, force is further linked to the charge. So you already see that the source of E is charge, the source of B and H, because H is proportional to B, at least in the simpler magnetic phenomenon, no hysteresis and all the other complications that we are bringing in at this point. So in those materials, B and H are simply related to each other by this permeability factor, and the source for this B or for H, as you can go back and check here, is this current that is flowing in a conductive path, and that current is what goes here. So this is the source for electric field is charge, and the source for this magnetic field and the magnetic flux density is current. Now we said that you have this epsilon r, right, which is the relative permittivity, but in scenarios where things are complicated, what we say is that we don't exactly obtain E. What we say is that in a material, so if I assume that this is a material, okay, just as B and H were related by a certain quantity, we say that charges produce not D but produce a D. D is further related to E in a material. E applies a force on the test charge, and this force is what you are able to measure, okay. And this vector field D, okay, all these are vector field quantities. So this vector field D is called as electric flux density, okay. Electric flux density tells you how many flux lines are coming out on a closed surface or the charge is emanating, and this flux density, if the material medium is very simple, it's just if the material medium happens to be vacuum, then it would be epsilon 0 times E, okay. Or if it happens to be a simple material which can be characterized by a relative permittivity epsilon r, then D will be equal to epsilon 0 epsilon r times E. Now you see the analogy between this and the magnetic materials, right. So you have B equal to mu naught mu r into H, okay, and this D field is measured in coulombs per meter square, okay. And the reason why we do this electric flux density is because if I take this charge, okay, look at how many lines are crossing a particularly closed surface. So you can imagine that there is a closed surface over here, and then calculate how many lines of fields are coming out of this, and repeat this experiment in another material, say water or something, okay, assuming that you are able to create an isolated charge, positive charge over here, then the flux lines will be different, okay. And this difference in the flux lines of air and this one is what we call as flux density D, that denotes that material must be doing something else, and our reasoning is that D is a mediating field. So you have charges, you have producing them as D related to E by the material properties. If it is water, then epsilon r will be different, if it is something else it would be different, and there is also a phenomenon of polarization which goes with D. I will mention that one in a moment, and that E will further exert force on a test charge that is brought, and that force is what you are able to measure. Similarly, in a magnetic phenomenon, you have these currents or whatever the sources of the magnetic field are, that produces B. B is related to H, okay. H produces further force or relates to the current, and then you are measuring that particular, or rather in this case it's actually B which measures you the force. So it's actually the current H produces B, or rather H is related to B, B is related to the force, okay. These E and B fields are further related to each other by what is called as the Lorentz equation. It tells you that if I take a test charge, then the force acting on this test charge, okay, will be given by, due to the electric component itself, some Q test into E, this E must be coming from some charge that is situated over here, plus if the test charge were to be moving with respect to some observer frame, then the amount by which it moves, the velocity with respect to it moves, and the corresponding magnetic field B, there will be a force on that. So you can see that the direction of the force would be along the same direction as the charge, but the direction of F, because of the magnetic field, will actually be perpendicular to the charge motion, because charge motion constitutes current. So far we have introduced all electromagnetic quantities. We have also looked at two laws. One is the Coulomb's law, which gave us this one, and then we have also looked at Ampere's law, okay. We have looked at Ampere's law in the integral form of the equation over here. So we have this Ampere's law in the integral form, Biot-Savart law is used to obtain the magnetic field from the electrical this one, so we don't really bother about that at this point at least. And then we say, or rather we write down this Ampere's law in a slightly different fashion. Okay, rather Ampere's law is actually given, I made a small mistake, the Ampere's law is actually given by, Ampere's law is not given in terms of B but rather given in terms of H over a closed loop. So H dot dl will be equal to the enclosed current, or you need to multiply this one by mu 0. If I were to express this one in terms of B, I should multiply this enclosed current by mu 0. Anyway, so we have seen this law, which is H dot dl is equal to I enclosed, and the corresponding point form of this is called as curl of H equal to J. What is this J? J is what we call as current density. Okay. Before explaining current density, there is another law which I would like to talk about, and that law happens to be that of counting this number of electric flux lines, as these are called as, counting the number of electric flux lines and recognizing that if I perform a closed integral of this quantity d over the closed surface, that will give me the total charge enclosed. So you can see that things are slightly similar to the magnetic case, that if I take the closed surface instead of the line and then integrate this flux density tells me how many flux lines are coming out per meter square. So multiply that one by meter square, in the sense that integrating will give me the total charge enclosed. So C by meter square into meter square should give me the total charge in coulombs, right? And in the corresponding point form, the equation becomes, okay, the corresponding point form, the equation becomes del dot D equal to rho V, where rho V is called as the electric charge density, or simply charge density. Okay. Now these equations are not new to you. We have seen in the previous module how to interpret these equations, right? When I write del dot D equal to rho V, I simply mean that if I take the divergence of D, which is a very valid physical operation that I am going to do, right? So I take a piece of closed surface and then evaluate the quantity d that would be normal to that surface, and then if I integrate over the entire surface area, if there is a source such as a positive charge or a tap with a water kind of a analogy that we have discussed, that source would be the charge density. So the source of d is the charge density. Similarly, if I take a closed path or a contour and then integrate h over that contour and then divided by the surface area and take the limit of that surface area going to 0, I obtain the rotation. So in a sense, that what we are seeing is that the source of this magnetic field, which would be this rotation kind of a thing, or the curl of the magnetic field, will be precisely equal to the contribution, or it is precisely equal to the amount of the current that this particular loop is enclosing. Okay. And the right hand side is giving you the total current, because the quantity current density, okay, is measured either usually in ampere per meter square in a general way. So if you integrate this one over the open surface, then you obtain what is the total enclosed current. So this is what you have as the current density, this is what you have the charge density. Charge density can come in three varieties. If I take a charge and then sprinkle it all over the space, I have the volume charge density. If I spread it around in a thin layer of this one, then I will be obtaining a surface charge density, which is measured in coulomb per meter square. And then finally I have a point charge density, which is just a point charge of vanishing location, mathematically a little bit of a complicated stuff. And then finally I have a line charge density in the form of a charge occupied in the line. Similarly, for the current density, the most common current density would be something that would be spread over the surface, changing along the entire surface, or it might be spread over a sheet of a plane. Okay, so this would be you have to imagine a 3D picture, but this would be a 2D picture. So on a piece of plane like a thing, if I start putting in the current vectors or the current density vectors, then that becomes a sheet current. In general, it is measured in ampere per meter square. Here it is measured in ampere per meter. Okay. The couple of additional laws which I have not discussed is this law, which tells you that the divergence of B is equal to 0, indicating that B lines don't really have any source. In other words, there are no magnetic poles or like poles or whatever, the south poles, isolated ones, which can give you this particular source for the B field, and hence del dot B is always equal to 0. So we have discussed 3 Maxwell's equations, although we have not discussed one of the most important equation, which we leave it to the next class. Okay, this is called as Faraday's law, and once we have Faraday's law, that will complete Maxwell's equation. Thank you very much.